Assalamu alaikum. Welcome back to our channel, Digital Future AI School. Kindly subscribe our channel, like and share with friends. And this is the episode 24 of Book AI Agent Makers, written by Mr. Zahir Ahmad Mir. Thank you for joining us. Welcome, everyone. Today we're cutting through all the noise, all the high-level theory about AI, and we are going straight into the deep end.
We're talking about the structural DNA, the actual blueprint.
Exactly. We're using 10 professional visual diagrams from the book, AI Agent Architectural Blueprints and Frameworks, to really unpack how these systems work internally.
Right.
So our mission today for you listening is to make you fluent in the language of AI architecture. We want you to be able to grasp not just the abstract concepts, but the concrete process for building these things.
It's about moving beyond what an LLM is.
And into how a full functional agent actually works.
Right.
From that very first user input all the way to a final safe output. It's really a shortcut to understanding the engineering side of this revolution.
And that's the key word, isn't it? Engineering. This is where the big ideas and the excitement meet the hard reality of building software. These diagrams we're looking at, they aren't just pretty flowcharts. They represent the international standard, both in academia and in the industry, for how you conceptualize and build agent systems.
So they're not just suggestions.
Not at all. They dictate how components have to interact, how data flows, where your critical safety checks need to be. It's the difference between a functional, scalable product and just a cool piece of code that falls over the second it hits a real-world problem.
Right, the theory versus the practice.
Precisely. We're analyzing structure, flow, safety, and the operational intent behind all of it. This is the architecture that underpins real, reliable intelligence.
Okay, so let's get into it. Let's start at the very core diagram, OPOT1, the core AI agent architecture. Looking at this, it feels like the internal planning, the step-by-step loop for pretty much any modern agent you might interact with.
It is the canonical diagram. And it establishes, I think, the most fundamental truth that people often miss. The element itself is just one piece. It's the reasoning core, but it's not the whole system.
It's just the engine, not the whole car.
Perfect analogy. This diagram maps that whole vertical journey of a piece of information. And it shows why the system absolutely must be tool-augmented and safety-focused to be of any real use.
So we start right at the top, with the trigger, the user input. That could be text, could be media, whatever. But the first really intelligent step, the one you're saying, is so critical.
Is the intent recognition engine.
Yes.
This is everything. This is where most agents succeed or fail, right at the start.
And its job is just to figure out why the user is here.
Exactly. Is this a command? Send this email. Is it a query for knowledge? What was the capital of Tunisia in 1980? Or is it a request that needs a tool, like calculating something with Python?
So the quality of that first little engine dictates the entire path.
The entire path. If the agent misunderstands the goal here, it doesn't matter how powerful your GPT-4 or your Claude 3 is downstream, the whole process will fail because it's solving the wrong problem.
And I can see how that would happen if a user types something like, can you draft an email about the Q3 report? A bad intent engine might just see email and try to send one.
A classic failure mode. It confuses the query with the command. The real intent is to draft and get approval. A well-tuned intent recognition model is trained specifically on that kind of nuance.
Okay, so once the intent is locked in, the diagram shows the flow splitting. It goes into two parallel paths.
And that word parallel is so important from an engineering perspective. They run at the same time.
So on one side, we've got reasoning and planning. This is the agent's brain, right? Figuring out the step-by-step.
That's the one. If the intent is find me the cheapest flight to Tokyo next month, the reasoning path designs the subtasks. Step 1, call the flight API. Step 2, filter the results by price. Step 3, check the dates. It builds the workflow.
But at the exact same time, you have the safety and policy guardrails.
The non-negotiable layer. You brought up an interesting point before we started. Doesn't running them in parallel add latency? And the answer is yes, sometimes it does, but it's a necessary trade-off.
For reliability, I assume?
For reliability, for compliance, for trust. The guardrails are checking the plan that the reasoning engine is producing. It's asking, is this plan safe? Does it violate any of our policies? Is it trying to access data it shouldn't?
So you can't just let the agent run off and start using tools.
Never. The plan has to be both ready and audited for safety before anything else happens. That's a conscious engineering decision that prioritizes trust over raw speed.
Got it. So the two paths converge. The plan is made, it's been verified, and now we hit the tool selection layer.
Right. Now the agent knows what it needs to do and how to do it safely. But this is where it decides which instrument to pick up. Does it need a web browser, a calculator, a specialized API?
And that feeds directly into the tool invocation system. The diagram lists a whole bunch of them.
It does, and the list itself tells a story about what a modern agent is capable of. You have the obvious ones. Web access, of course. Python for any kind of complex calculation or data analysis. And file search for looking through internal documents.
But there are some more specialized ones here. Canonmore, what's that?
So in the context of the book's examples, that's likely a proprietary tool. Think of it as a super high-fidelity search system designed for massive internal documentation libraries, highly specialized.
Okay. And then you've got Imagen, so it can create things, and then more general things like automations and APIs.
Exactly. And that just shows the agent isn't a solitary thinker locked in a box. It's an operating system that connects to the entire digital world.
Now, there's a really important line in this diagram, a horizontal one, the feedback loop that connects the tool selection layer back to memory.
Yes, the learning mechanism. This is so critical.
And it's split into long and short-term memory.
Right, so short-term memory is easy. That's just the context of the current conversation. It's the RAM for the task, so it remembers what you just said.
But long-term is different.
Long-term is where the real learning happens. It's knowledge retention. Often, this is where a RAG system, which we'll get to, plugs in. It stores what it learned from past tasks. Which tools worked? Which ones failed? What facts did it verify?
So before it picks a tool, it checks its memory.
It must check both. It looks at the short-term context, what are we talking about right now? And the long-term knowledge, have I done something like this before and what happened? That's how it avoids making the same mistake twice.
And after all that, the tools are used, the data's gathered, we get to the end of the loop. The raw info goes to the output generator.
And this isn't just a print statement. This step is about communication. It takes all the raw facts and data and structures it into something that is structured, clear, and safe, which finally becomes the final response for the user.
A complete self-regulating cycle.
That has to work perfectly at every single stage.
So that's the machine's anatomy in Diagram O1. But what's the assembly manual? Diagram O Type 2 gives us the 10-step framework for building agents. This seems to be the blueprint for turning that architecture into a real project plan.
It is. This is what separates, a weekend project from a professional grade system. What this diagram makes crystal clear is that building agents is software engineering. It requires discipline. If you skip a step here, you're just guaranteeing it will be unstable when you try to scale it.
Let's spend some real time on this. We can group them into phases, maybe starting with the first 3 steps, which seem to be about definition.
Good idea. So, step 1, define agent role and purpose. You cannot write a single line of code until you have a crystal clear, singular mission statement.
What's its job?
What is its one job? Is it here to optimize the supply chain? Is it generating marketing copy, performing medical triage? That definition dictates everything that follows. The tools it needs, the cost, the ethical rules it has to follow.
A fuzzy role leads to a fuzzy agent.
An agent that does everything poorly, precisely.
Okay, step 2. Structure inputs and outputs. This feels like one of those things people forget until it's too late.
Oh, it's so often an afterthought. But this is the data contract. You have to decide up front. Is my input going to be a clean JSON object, a messy PDF, raw text? And what about the output? If it needs to feed into another system, it better be predictable, structured JSON.
You're defining the borders of your system so it can talk to everything else.
Exactly. It ensures a seamless handoff.
Then step 3 in this phase, select appropriate model. This is choosing the engine. The diagram lists GPT, Claude, Gemini, Llama.
And this choice is a major architectural decision. It's a complex balancing act. You're trading off raw reasoning power against cost, speed, and privacy.
So for a simple task, you don't need the most powerful, most expensive model.
Exactly. If you're just summarizing text 1,000 times a minute, you might pick a smaller, faster, much cheaper Llama variant.
Yeah.
But if you're doing complex, multi-step ethical reasoning for a legal agent, you're going to pay for the state-of-the-art model.
Okay, that's the definition phase. Now we move into the mechanics, steps 4 and 5. This is where we actually start building things.
Right. Step 4 is configure tools. This is the practical implementation of that tool invocation system from the first diagram. You're not just listing tools, you're writing the code that connects to them, that handles authentication.
You're giving the agent its toolkit.
You're literally writing the API documentation for the agent itself so it knows its own capabilities. Connecting it to an OCR tool to read invoices or to whisper for audio transcription. This is that step.
And then the really complex part, step 5, design reasoning flow.
This is the brain surgery. This is where you design the chain of thought logic. It's where you program the intelligence. You're mapping out the decision tree. If the user mentions billing, first execute tool A to get the invoice, then validate the result with tool B, and only if B passes, execute tool C.
So this is where a lot of the actual programming and prompt engineering happens.
It's the core of it. This flow design is what ensures the agent follows a predictable, verifiable path to a solution. It stops it from just wandering off.
Okay, finally, phase 3, validation and scale. Steps 6 through 10. This feels like the enterprise-grade stuff.
This is what makes it a real product, and step 6 is becoming more and more critical. Add human-in-the-loop review.
The safety net.
The essential safety net. When the agent is uncertain, or when it's about to make a high-stakes decision like transferring money, it has to stop and flag it for a human. This builds trust, it manages risk, and it provides an invaluable feedback loop for retraining the system.
It's ethical oversight, built right in.
It has to be. Then step 7 is memory integration. We talked about memory in O.1, but here is where you actually build the pipeline. You set up your vector databases, you implement your AuG system, and you make sure that learning persists between sessions.
So it remembers what worked last time.
So it can immediately draw on its past successes and failures.
Step 8 is the one everyone dreads but needs. Test and validate.
Oh, it's grueling. And you can't just test the happy paths where everything works. You have to actively try to break it. You test with ambiguous queries, malicious prompts, and high-stress scenarios.
What happens if 10 people ask for the same tool at the same time?
Exactly. Does it crash? Does it queue them up? Does it fail silently? You have to know the answers to those questions before a customer finds out for you.
Then step 9, automate and scale. This is going from your laptop to the real world.
This is the leap. Moving from a proof of concept to a production environment that can handle thousands of users. This is where you bring in robust infrastructure, things like Kubernetes or serverless functions, to make sure it's reliable under heavy load.
And the final step, step 10, which I guess is never really final, monitor, improve, update.
Because an AI agent is a living system. It's not a piece of software you ship and forget. You have to constantly monitor its performance latency, accuracy, how often its tools are succeeding. You need to detect when its performance starts to drift and be ready to push updates.
So these 10 steps are the entire circular life cycle of a professional AI agent.
It's the whole journey, from idea to a mature, evolving product.
Okay, that framework is the generic playbook, but now we need to get into specialization. As diagram O.3 shows, not all agents are the same. This is where it gets really interesting, because we're seeing how complexity scales across 3 core categories.
And this is such a critical first filter for any project. You have to know which category your agent falls into, because you can't just apply the architecture of a simple text agent to, say, a complex multimodal challenge.
So let's start with that base layer. Text agents, reasoning.
These are the purists. They live and breathe language. Their job is analysis, synthesis, and creation based only on text.
And the examples here are things like a legal agent that analyzes case law, a startup planner generating business models,
or a script generator. They all excel in tasks where the input is text and the output needs to be structured, well-reasoned text. They're the synthesis engines, relying heavily on the LLM's raw reasoning and usually a good RAG system.
Then we level up in complexity to multimodal agents. These are the ones that break out of that text-only world.
Right, and they bring with them the added complexity of pre-processing pipelines, which we'll get to in a moment. Their whole job is to deal with data that isn't text.
Like an OCR document agent that reads scanned images, or an audio-to-text tutor that listens to a student.
Or a vision-based checker analyzing a video feed from a factory floor. The core challenge for all of them is translation. How do you turn pixels or sound waves into a structured format that the language model can actually understand and reason about?
And then we get to the top tier, the highest level of independence, autonomous agents.
The key differentiator here is that word, autonomy. And it's enabled by one core capability, the ability to self-correct.
What does that mean in practice?
It means if a tool fails, say an API is down, a normal agent stops and reports an error. An autonomous agent, however, looks at the error, reevaluates its plan from step 5, and tries a different approach. Maybe it tries a backup API or decides to search the web for the information instead.
So it doesn't need a human to intervene when something goes wrong?
Minimally. Examples like a self-correcting agent or an automated researcher imply that they can operate for long periods without oversight. That self-correction loop is what defines true autonomy.
Speaking of making agents more reliable and fact-based, let's dive into diagram O.5. This is the RAG knowledge system, or retrieval augmented generation. This feels absolutely essential for grounding an agent in reality.
It's the architecture that gives an LLM an evidence-based backbone. It's how you bridge the gap between the model's general, often outdated training data and your specific proprietary real-time information. It's the anti-hallucination machine.
The flow here starts with a user query, but it immediately gets converted into something called an embedding vector. Can you break that down for us? What actually is that?
It's a fascinating concept. An embedding vector is basically a list of numbers. It's a mathematical representation of the meaning of the user's query.
So it's not about keywords.
Not at all. It's about semantics. Imagine a giant multi-dimensional map where related ideas are located close to each other. The query, how much did we spend on marketing last quarter, gets turned into a vector, a point on that map that is mathematically very close to documents about Q3 financial reports or ad campaign budgets.
So it's searching for conceptual similarity.
Precisely.
Yeah.
Which is so much more powerful than just keyword matching. And that vector is what gets sent to the vector database.
And the diagram lists a few of these. FaceS, Chroma, Weaviate, Milvis.
These are the specialized libraries for this. Their database is built from the ground up to store and retrieve these numerical vectors at incredible speed. Some, like FaceS, are known for being lightning fast. Others might offer better cloud integration or other features. They're the memory banks of the RAG system.
Now, one thing that's implied here is the idea of chunking the data before it even goes into that database.
A critical engineering step. You
Yeah.
can't just dump a 100-page document into the vector database. You have to break it down or chunk it into smaller pieces.
And the size of those chunks matters.
Hugely. Do you use small, dense chunks of maybe a couple of sentences? They're great for finding one specific fact with high precision. Or do you use larger chunks of a few paragraphs? They're better for preserving context, but might include irrelevant information. It's a constant tuning process.
Oh, okay. So the vector database finds the top relevant chunks of your documents.
It finds the evidence. And this is the magic of RAG. The system retrieves those chunks, and then, this is the key, it passes that evidence to the LLM along with the original question.
So the LLM isn't answering from its own memory.
It's forced to answer based only on the evidence you just gave it. It becomes a very sophisticated summarizer of the provided facts. And that's how you get a reliable, verifiable, grounded response.
That makes so much sense. Okay, let's shift to how we handle the other kinds of data. Diagram 0.6, the multimodal processing pipeline. This shows how you take something messy like a video and prepare it for an agent.
Right. If your agent is going to interact with the real world, it needs senses. This pipeline is how you give it sight and hearing. The ultimate goal is to translate all that raw sensory data into the clean, structured text that the core agent architecture understands.
Everything has to become language for the LLM.
Everything eventually becomes language. So you start with these diverse inputs, image, audio, video, and each one needs its own specialized engine.
For image, the diagram says we use an OCR engine, like Paddle or Tesseract.
Industry standards for optical character recognition. Their job is to look at an image of a document and pull out the text, turning pixels into characters the agent can work with.
For audio, it's Whisper STT.
Which is an incredible speech-to-text model. You can handle multiple speakers, background noise, different accents, and turn it all into a clean text transcript.
And then the most complex one, video. This uses something called FFmpeg frame extraction.
A video is just a huge sequence of images and an audio track. You can't feed all of that to an agent. It's too much data. So you use a tool like FFmpeg to strategically pull out key frames moments where something important changes, along with the synchronized audio.
So you're sampling the video for the important parts.
Exactly. And all of these processed bits and pieces, the text from the OCR, the transcript from Whisper, the frames from the video, get standardized into a clean processed input.
You're cleaning it all up, removing the noise.
And formatting it consistently. This clean data payload is then what you feed into the AI agent to be used for its core loop of reasoning, tools, and memory.
It's easy to look at all this RAG systems, multimodal pipelines, 10-step frameworks, and just assume it costs a fortune to even get started.
A very common assumption.
But Diagram 04, the free tools ecosystem, seems to push back on that. It's a map for building a full stack with no code or free components.
And this is what's so transformative about the current moment in AI. The democratization of the tools. This diagram lays out 3 pillars that show how anyone with the time and curiosity can start building incredibly sophisticated agents without massive upfront investment.
So the first pillar is multimodal tools.
These are the open source powerhouses. We see OCR, Paddle, Tesseract, and Whisper, audio again, which shows how foundational they are. But then you also have things like OpenCV for advanced computer vision, and stable diffusion for generating images. These give you enterprise-grade capabilities for free.
The second pillar is the nervous system connecting it all, automation platforms.
The glue. Platforms like Zapier, Make, and especially N8N, which is open source and can be self-hosted. These are the workflow executors. They listen for trigger, a new email arrives, grab the data, send it to your agent for reasoning, and then take the agent's output and perform an action, like updating a spreadsheet.
They let your agent actually do things in the world without you having to code every single integration.
Exactly. They handle that automate and scale step for you.
And the third pillar, which is huge for privacy and cost, local AI.
This is all about running models on your own hardware off the cloud. Tools like Llama and LM Studio make it incredibly easy to download and run powerful open source models locally.
And the benefit there is twofold.
Twofold. One, cost. You're not paying a per token fee to a cloud provider. Two, and this is huge for businesses, is privacy. The data never leaves your network. You can even run your RGES systems locally with FAIs or Chroma. It's a game changer for working with sensitive information.
So we've covered the single agent, its tools, its brain. Now we need to scale up to solve really big problems. Diagram 0.7 introduces multi-agent team collaboration. This isn't just one agent anymore, it's a virtual team. This feels like the future.
It is absolutely the future architecture for complex problem solving. It's a direct answer to the limitations of a single agent. No matter how powerful a single LM is, it's still a single point of failure. It can get confused trying to juggle too many roles.
So you mimic a human organization.
You mimic a highly functional human team. You get specialization, you get reliability, you get checks and balances.
And at the top of the hierarchy, you have the manager agent.
Yeah.
The conductor.
The project manager. Its only job is to take a big, high-level request like analyze market trends for electric vehicles and break it down into smaller, solvable tasks for its team. It has to decide who does what.
So it delegates. Research agent, go find these reports. Drafting agent, format the output.
Exactly. And just as importantly, it manages the communication protocol between them. It ensures everyone is speaking the same structured language, usually JSON, so there's no ambiguity.
Okay, so below the manager, we have the specialists. First, the research agent.
This one is all about data gathering.
Great.
It's an expert at using tools, web search, database queries, RAG systems. Its only tasks are finding facts and producing summaries. It lives and breathes information retrieval.
And working alongside it, we have the drafting agent.
This one specializes in communication and presentation. It takes the raw summaries and data points from the research agent and turns them into a polished, structured document. If the final output needs to be a PowerPoint deck, this is the agent that builds it.
It's the presentation layer.
It's all about clarity, structure, and adhering to the required format.
And then before anything goes out the door, there's a final gatekeeper, the quality control agent.
The indispensable final reviewer. This agent checks for consistency, it checks for factual errors against the source data, it checks for grammatical mistakes, and it ensures the output adheres to all the safety guardrails we talked about.
So it's another layer of safety.
It's a critical one. It dramatically reduces the chance of a mistake reaching the end user. It's the proofreader and the fact checker all in one, which allows the system to produce a final approved output.
If that multi-agent system is the blueprint for future collaboration, then Diagram 0.9, the business automation workflow, is the blueprint for what's happening right now. This is how agents are being plugged into real companies today.
This is the practical rubber meets the road diagram. It shows how you take that intelligent reasoning core and embed it into a company's existing processes to create real value. It's the end-to-end automation cycle.
The workflow kicks off with a start trigger from the real world. A user input from an email, a form, or a website event.
Right, something happens. A customer fills out a support ticket. An invoice arrives in an email. And that event is picked up by an automation platform, our friends Zapier, Make, or N8N, which acts as the trigger.
That platform then packages up the data.
And sends it to the intelligence layer. Send data to ChatGPT, or any similar model. This is where the agent does its core reasoning loop from Diagram O.1. It figures out what the email is about, extracts the key information.
Like the vendor name and amount from an invoice?
Exactly. And then it writes a structured output, a clean payload, saying what to do next.
And that output goes to the action layer. This is where the agent actually affects the business.
This is what turns reasoning into ROI. The agent's decision triggers an action. Update the CRM, add a row to Sheets, call another API, send an automated email. This is the agent moving data and making decisions across the company's software stack, which produces the final business output.
Let's make this even more concrete. Diagram O.8 gives us a specific use case. The digital AI school architecture. This is a perfect example of that specialization and collaboration in action.
It's a beautiful illustration of the principle. Instead of one giant monolithic teacher AI that would be mediocre at everything, you break the problem down into 3 distinct specialized roles.
Okay, so under the main digital AI school umbrella, we have 3 agents. The first is the AI teaching agent, Lessons.
This one is the content expert. Its job is curriculum delivery. It generates exclamations, it creates lesson plans, and it can adapt the difficulty based on how a student is performing. It needs a massive RAG system loaded with pedagogical material.
Then you have the AI assessment agent, MCQS tests.
This is the evaluator. It's an expert in generating fair, accurate test questions that align with the curriculum. It handles the grading, providing unbiased, instant feedback. Its reasoning is highly constrained to verifiable facts.
And third, there's the external-facing agent, the AI parent communication agent.
The diplomat. This agent's job is to take all the raw performance data test scores, time on task, and translate it into clear, empathetic, and personalized progress reports for parents. It specializes in communication, not pedagogy.
And the key is that all 3 of these specialized agents are feeding their data into a central hub.
The student progress system. That's the brain that synthesizes everything. And the whole system works together towards a single unified goal: personalized learning.
So if the assessment agent sees a student is struggling with the concept,
It updates the progress system, which then instructs the teaching agent to generate a remedial lesson specifically for that student on that topic. It's a level of personalization that's just impossible with a one-size-fits-all approach.
incredible. Okay, we have covered a massive amount of ground. We've seen the architecture, the workflows, the specializations, the real-world applications. Let's bring it all home with the final piece, the money. Diagram O10 is the AI agent monetization map.
The commercial context. Because all this sophisticated engineering has to translate into sustainable value, this map lays out the 3 primary ways you can turn these blueprints into a real business.
The first path is high-touch and custom services.
Right. This is building custom agents for specific clients with unique problems, like the business workflow in 0.9, or it's high-level consulting, advising companies on how to design their own multi-agent teams based on 0.7. It's high-margin work because you're selling your time and expertise to solve a very specific, high-value problem.
The second path is more about scale. Digital products.
This is where you package your expertise into something you can sell over and over. This could be pre-configured agent packs like an agent that's already trained to summarize legal documents for small law firms, or even simpler things like prompt templates that guarantee a specific structured output. You're selling the IP.
And the third stream, which is often the goal for a software business, subscriptions.
Recurring revenue. This means offering monthly plans for access to your proprietary agents. And just as importantly, you're selling access to AI updates. We know from step 10 that these are living systems. Customers pay a recurring fee to ensure their agent is always secure, always optimized, and always using the best underlying models.
They're paying for reliability.
And continuous improvement. And as the diagram shows, all 3 of these paths, services, products, subscriptions, all lead to the same goal: scaling IP.
And the quality of the engineering from the first 9 diagrams is what makes that possible.
It's a direct link. The robust architecture from O point, the evidence-based grounding from AIR in 0.5, the reliability of a multi-agent team from 0.7, that's what creates the value that people are willing to pay for month after month.
Wow, what a journey. We've just done a complete teardown of the structural DNA of the modern AI agent. Let's just quickly recap the absolute key takeaways. We start with that foundational architecture in O1, seeing how input has to pass through both reasoning and safety before it ever touches a tool.
Then the 10-step framework in O2, which hammered home that this is disciplined software engineering.
We saw the need for specialization in 0.3, how a RAG and 0.5 grounds agents, in fact, and the complex pipelines in 0.6 needed to handle real-world data like video and audio.
And then we scaled up, looking at multi-agent teams in 0.7 that gain reliability through delegation and saw how they plug into real business workflows in 0.9.
All leading to the monetization map in 0.10.
And if you put it all together, I think the fundamental truth that these diagrams reveal is that building successful AI agents, it's not about magic. It's not about finding one perfect prompt. It's about modular, structured, disciplined engineering.
It's about connecting the right pieces together.
Connecting the right tools, maybe from the free ecosystem in 0.4 to the right architecture from 0.1. to achieve a specific business outcome from O10. That's the real skill.
So to leave our listeners with something to think about.
Here's a provocative thought for you. We discussed the autonomous agent in diagram O.3, the one that can self-correct. And we discussed the multi-agent team in O.7, led by a manager agent.
Right.
What happens if you give a self-correcting autonomous agent the high-level goal of optimize this entire business process? And what if it calculates that the most efficient way to do that is to design and deploy a new multi-agent team? How long until the manager agent from diagram O.7 is no longer a pre-programmed part of the system, but is itself one of the temporary outputs of the self-correcting agent? What is the limit of autonomous self-optimization within these frameworks? At what point does the blueprint start designing itself?
Something to really chew on. Thank you for joining us for this dip dive into the blueprints of intelligence. We'll see you next time.